that was excellent. Now, how to improve the performance of the DRAM device? So in order to improve something, we need to know what makes it better, or how we measure a performance metric over there to say that this is now better than previously. So the DRAM performance is defined by the bandwidth and latency. What is the bandwidth? So these are two important metrics, bandwidth and latency, to measure the performance of the DRAM device. What is bandwidth? Speed in transferring the data. Not only speed, but should be also amount of data at which we send it, right? So at the speed where we send these data, it means amount of data divided over time, okay, per second. And normally we measure it as a mega transfer per second. Now, what is latency? So bandwidth, we could send like 64 bits every once in a while, for example, right? That is a bandwidth. But now the latency itself, how we make the things faster? We access the same row repeatedly, right? But with different columns, for example. This way we save a lot in pre-charging. So we open the row, we access it. Now next time we access the same row, but different columns. This way we can make the latency very minimal, although we still access column by column every time. How we make the latency higher? By accessing different rows. We access the first row. We now pre-charge it, closing the row. Now we want to activate another row, right? So we want to bring it to sense amplifier, read it, send it to the data bus, and then pre-charge again. That's latency is different than the previous scenario, for example. And the previous one was shorter because we didn't do pre-charge to every request. We are reading the exact same row, but different columns. So latency is basically when I send requests from the memory controller to bring me the data, and then when I get the data, that's time for round trip is the latency itself, which is the delay in which the memory device is going to supply me with the data that I requested, or the time it takes for the memory controller to receive a response after requesting data from the DRAM. Is it clear? All right. Increased bandwidth, if I'm increasing the speed at which I send data, it means higher latency. Why is that? If I'm increasing the bandwidth, the amount of data I'm sending at the same time, it means higher latency and increased power consumption. The power consumption is clear because whenever I increase the frequency in the interconnect, I always need higher frequency to squeeze more data. If I'm getting this data, not in this clock cycle, but I'm shortening the clock cycle, for example, in here. If I shorten this clock cycle even a little bit, I have to change the frequencies right away, okay? Because I need to make it now double of that amount. And then double, 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 all the way until I satisfy the one link. But why higher latency? Why, when I increase the bandwidth, I increase the latency? Excellent. Or what if I change the row size? Now the row size becomes larger, right? Imagine I change the architecture of the DRAM. I make the row larger, and the chip now is providing, instead of 8 bits, 16 bits, for example. What will happen? I need a decoder that is larger, right? That's in terms of number of columns because I increase the size of the row. But also if I increase the number of rows in the chip to fit more data, to increase the capacity, I also need to change the decoder to decode the row where I need to fetch the data. But not only that, I also need to increase the size of the row amplifier or the row buffer, the sense amplifier, right? Increasing all those hardware would require more time to fetch more data, right? And also it's expensive, reducing energy and so on. But also, you could increase the number of chips. for example, to provide more data. Imagine that, forget about the interface, the 64 bits. What if we increase that interface and want to increase more chip? That will also cause to increase the latency, although all of them operate in the same clock cycle. But now that clock cycle is going to change. Okay? This is an important figure showing the progress in terms of capacity, bandwidth, and latency. What do you expect? Is it always increasing, decreasing? Think about the DRAM you have in your computer, how it was 10 years ago. What was the size? Very small, like 1 gig in maximum. Then it moves to 2 gig. It moves gradually to 4, 8, 16, now 32 on that range, right? So it's always increasing. How about the bandwidth? It's also increasing, right? Latency, reduced. Now, which one is faster in terms of improvement? Remember the example, the difference between the bandwidth of DDR4 and DDR5. Was it doubling? You remember the figure we show in last lecture, where we moved from DDR4 into DDR5? We see that there are very little improvement in terms of the bandwidth. So the capacity is really improving almost linearly, and it's getting even cheaper, right? But the bandwidth is almost saturating. The latency is a little bit increasing, but in very smaller pace compared to the capacity, for example. Why is that? Remember in the first line when we mentioned about DDR5, we said the latency is almost the same as DDR4 and DDR3. Okay, so this is important to keep in mind. The latency, there is some point we cannot get much of improvement on that. We try to increase the number of capacitors, but by the end of the day, the interface is restricting us from getting more data as we want. So we are limited by the end of the day by only 64 bits. So the latency to send those bits in the interface is almost constant among all of them because they are using one channel and we are accessing the same number of DRAM chip and all of them accessing single location in a bank and give us all those data, okay? Same as we did in the cache. So in the cache, we were improving a lot of things. For example, the number of sets in the associativity, right? Or we could increase the cache itself, the capacity size. Same in here, we could increase the bank size. We could increase the row buffer or improving it, sensing more. We could utilize advanced process node to enhance efficiency and speed. So advanced process nodes related to the transistor level itself. We said at each cell, we need a capacitor and transistor. And transistor could be smaller, so we could fit more cells, right? Increasing the size of the interface. This is not happening until now. We are only increasing now the more bits for ECC, for example. But we're still dealing with 64 bits until today. Can we increase it more? Can we make it 128? Could be. Yes, please. Yes.
Motherboard, it has 4 DIMMs for RAM, but it was not recommended to do so. One of the reasons is that either do so by buying or deriving or their own how format is so I it both channels what would be happening.
Excellent question. Did you understand the question? So you are allowed to add 4 DIMMs into your motherboard, but it's not recommended to do so. It's recommended to double the size of single DIMM rather than adding 2 DIMMs, for example. It's better to double the size of the 2 DIMM rather than adding 4 DIMMs to the motherboard. Why is that? Why it's better to have a larger capacity single DIMM rather than having two DIMMs with half capacity and half capacity. For example, you have 8 GB in one DIMM. You purchase another 8. You purchase another 8, another 8. Which one is better, to have 4 8 GB DIMMs or single DIMM with 32 GB? Single one is better. Why? So first, there's congestion in the data you get from several DIMMs. The first thing you have to understand, how many memory controller first we have in the CPU, okay? If we have multiple, this will make things way different because each of those will be isolated system. So you can communicate with all of them in the same time, and you get data from all of them at the same time. So we don't have any issue here. If we have single memory controller, what will happen? You have to get data from here. All the rest are idle, doing nothing. Although you add them, you pay money for them, but they are doing nothing because memory controller can communicate only to this, wait, get data, communicate to this, get data, and so on. Although you can overlap many of the things. So you start from the first DIMM at the clock cycle, right? You send a request from memory controller. Maybe you get the data at some point here because there's always latency to service your request. Now, within that time, after you get the data, you need to pre-charge, right? You need to refresh that row because you already perturb the row itself. You already altered the data itself. So you can, while waiting for those housekeeping stuff, you can send another request to the other DIMM. So in this way, yeah, you can overlap some of the time. So you don't really need to wait the double, like waiting for the first DIMM to service your request fully, and then you ask for the other one. But the benefit you get compared to the price you pay is really not that beneficial. That is one thing related to the outside world. Now, if you look into the single DIMM itself, what will happen if it is really larger capacity, meaning that it fits more data, meaning that you might need the same row again and again. So you activate one row, it's already in row buffer, and now you're going back to get the same data again. So you will find it most of the time because it's already in the row buffer. Now, if that data does not fit in that row, and your DIMM, for example, is small in capacity, so the rows might be smaller, or you have less number of rows, then you have to access multiple banks or multiple chips or multiple DIMMs to get larger data, right? In this way, you are also losing some benefit or some opportunities to improve the accesses. That was a fantastic question. Thanks a lot. So that's the beauty of this course. You will see most of these things really in your computer, in your own life, once you deal with that. Okay, any question? But remember, all those optimization, we call them optimization, but in fact, they are really design choices. So only the one who can change these things is the manufacturer itself, the company who produced the DRAM. And it's not only that, but also will have significant impact on the DRAM system cost, because changing the capacity, adding more chip, more channels, more memory controller, and so on, it's all going to impact the silicon area that you are consuming. All right, so we always keep saying this is design choice, this is the company can do it, but how they do it? So this question is from the book that we recommend for the course. Do you remember the name of the book? What is the name of the book we're using for this course? Who are the authors of the book? Maybe that's easier. Patterson, excellent. Who else? Hamming? No, not Hamming. Yes? Wow. The other one, Patterson, yes, that's correct. The other one, oh, Patterson is more famous than the other guy. The other guy was president of Stanford. So that's a homework for you, okay? One of them in Google, one of them the president of the university, So please check this question in the book. You can copy the text and you will find it in the book. This is really kind of debate. Which one is better? To have a chip in the DEM module giving you 8 bits or 4 bits or 16 bits. Now remember, we need 64 bits all the time. So if we have 8, that's going to dictate the number of chips. So we need 8 of them. If we have 4, we need 16 of them. If we have 16, we need maybe 4 of them or 2. 2. No, 4. 4. Who say 2? 16, 16, 16, 16. That's 64, right? Okay. So which one is better? By the end of the day, I'm getting 64 bits, so it doesn't matter in terms of bandwidth, for example. Remember those separate chips, right? Really isolated from each other, although they share the 3 things, since they are in the same rank. They share the data, the address, and the command. However, each of them requires certain amount of energy. So each of those has its own energy consumption. Now that is a very important metric, because if I add too many of them, like 8 of them or 16 of them, and they consume much more than what I have in 8 bits, that's going to consume a lot of power in terms of the total DEM. And then to consume the power that the entire motherboard is consuming, and probably it's going to affect the temperature of the motherboard and so on. So to answer this question is really not easy. You need to know the internal of this chip and how the clocking is connected to those and so on. For that, you can access this Excel sheet. There's a link in the book, but the link is not working anymore. If you open it, you will not see it. Okay, it will point you to Micron, which is one of the companies that's producing this DRAM. So I updated the link for you. This is updated one. You can open it. You will see several sheets, several Excel files. Okay, you can choose based on the technology. You'll see DDR1, DDR2, 3, 4. There's no 5, unfortunately, but you can at least choose 4. Right? You'll get an Excel sheet. In the Excel sheet, you'll see a tab called configuration. Based on that configuration, you can choose those numbers and send me the screenshot, what you'll get as a result out of it. So you just play with the configuration. It's automatically update the things internally. You'll see a lot of sheets in the Excel, and you'll see all the numbers get updated, and will give you several parameters about the cost that you are going to pay for each of those designs. Okay, it will ask you a lot of questions: how many pins you want, how many chip, how many bits out of each chip, how many banks, and all these questions. So feel free to play with it and send me a screenshot. You may get a bonus out of it. Okay, not a chocolate this time, but a bonus. Who likes chocolate? All of you, right? Who likes extra grades? All of you. Okay, maybe we can do both. Depends on how many students will send that screenshot. All right? I think so. I think so. I think so. So the interface is standard, right? But the parameter you send, it's really different. For example, we talk about refresh rate. Who's doing the refresh? The memory controller. If I need to do it faster, then the memory controller should do something to send more requests, right? And remember, when I send refresh command, it means the memory controller is blocked from sending any instruction or any command. Cannot send anything for that period of time because the DRAM is busy doing the housekeeping stuff or refreshing all rows, right? So of course, it's going to impact the memory controller or the CPU. And they should to communicate together for having correct workflow. Any question? Any questions so far? Yes. Extra? Raise your voice, please. Yes, yes, that's favorable, but you can still have the 2 or 3 or 4. You may get some benefits. Where's the figure? I think this one, because we are going to overlap the requests to get the data. So it's not like you need to wait for the first DEM to be fully processed and then you ask the second DEM.
My question, didn't have a strong thought, that thought that is strong thought. If we have multiple techniques, each one would have a different thought. So when there are bandwidth, then we increase this, then we have other things. Multiple when you program
Excellent question. Excellent question. Did you understand the question? So your classmate is asking, if we have 16 gigabyte one DEM, is it better to have another 16 or just replace that 16 DEM fully, remove it, and add 32 gigabyte? Okay. Now he's saying that the DEM is operating in its own clock cycle, right? And the other DEMs also work on its own clock cycle, meaning that they are independent. They can work like really at the same time, and each of them provides 64 bits. That's 128 bits per clock cycle, which is better than having a single DEM with larger capacity that only give me 64 bits again, right? Because the same interface. That's a very strong question, very valid one. But that is also go back to the CPU architecture. How many memory controllers do we have? If there's one, how many channels now do we have? If there's again one channel, I cannot do anything about it. Even both of them give me data, where to place that data. I should place it through the channel. Now the channel only fits 64 bits at the time. So I have 64 bits from the other side, but it cannot fit. So I have to sequentially push it. The first 64, then the second 64. I cannot have both of them at the same time, unless I have two memory controller or two channels, right? You remember the mesh topology? Then I can alternate between the DIMMs. I get this one, then this one, or both of them in the same time if the topology allows for that, right? So if you have two memory controller, two channels, it solves the problem. It doesn't matter now. Doubling or having two of them, it's still the same thing, same effect. You can access both of them in parallel, and maybe it will be much better than even doubling the size. Okay? You understand the question? You understand the answer? This is really important. Okay? That's why I show you all those pictures. Although might not be relevant to the course, like you're not really designing this DEM, but it's really important to understand how it works, and I'll leave everything else to your creativity. So you can come up with your own architecture, assuming that everything is correct, you can fetch the data at the correct time, and so on. And this is how you start doing research in memory device. You have to understand what is happening in the DDR4, and then you can change anything in it. You literally can play with the device. You can do whatever you want with it, okay? Assuming you maintain the parameter for activating a row, charging, discharging, and all these parameters. We discuss about ref I, which is refresh interval, right? This is one of the parameters that you need really to meet when you build your own system for the memory device. So there's a certain amount of time where you need to send requests every interval of those time. You have to send the request, stop sending other requests, wait for the DRAM device to do the refresh rate, and then you can continue doing so. If you do that, everything is correct. Then you maintain the correct data in the DRAM, and so on. All right, so hopefully you'll do this exercise. This is for you. There's no correct or wrong answer.
the middle.
So this Excel is from micron.com. I created an account over there, and then I selected DDR4, and so it allows you to like see the power consumption for your DRAM. And once I selected DDR4, like the Excel was downloaded, and this particular Excel, it has like the instructions for use. And like these are the DDR4 specifications, but I have kept like these details blank because I was not sure like about these terms, IPPO0 and things like that. One of the main tabs is this DDR4 SDRAM configuration. So here, the DRAM die density, this represents like the density of the package. So package is nothing but like the chip wafer that you have on your circuit board. So here 4 gigabits is the density of the die, and this can be like changed to different types. So 16 gigabits in the sense 16 by 8, it means 2 bytes. So one package is giving you 2 bytes of data. And here the next one is the DRAM width. So I was not sure what is that. So I just searched it up, and DRAM width means the amount of data that comes to the data bus from each of the chips. So that is like 8 bits per chip. So in one rank, if you like have multiple chips, so each chip is going to give you 8 bits of data. And the speed grade is the speed at which the data is going to get transferred. I think that is what. And there is this DBI mode enabled, which can also be set to on and off. From what I understood, this DBI mode is the how we can pre-charge a row buffer. So if it is off, that means it like waits for all the bits to be consumed from that row buffer, and like that takes up some time. And if you select like DBI mode to be on, then that helps to like save power overall, because like once certain amount of bits in the row buffer get used in the data transfer, then we just do the pre-charge. And this is another thing called package used. So there are 2 types here, SDP and DDP. So SDP stands for single data package. So there is only one wafer. And DDP stands for like dual. So you have 2 packages on top of each other. So in our case, if at all the per package, if the amount of data is 2 bytes, so if you're using DDP2R, then that means total you're getting 4 GB of data. 4 gigabytes. So once you enter these values from the DDR's configs tab, then the power calculation automatically like comes, because they have like designed the Excel with the formulas. This is the summary. Let me zoom. Okay, so the summary tab also shows the same thing about the total DDR SDRAM power that is getting consumed, which is 9.7. So this is for one DIMM. And this is the second rank power.
So in your experiment, which configuration was the best in terms of power consumption?
So I was like going for less power consumption, but still like a sufficient amount of storage space. So like the total storage that we got for the DIMM in total was 64 GB. And I have chosen like the number of ranks to be 4. And again, this is from the DDR config, the slide, which all of this is coming. And then the power consumption was 9.7. But let's say if I increase this package config from X8, let's say if I want to get more data in the data bus at once. So let's, if I go here and I select into 16. So at 16 bits per from a chip at once. So because of that, if you notice, the power consumption has drastically increased. It has become double because we are getting double the amount of bits from the same chip.
Right.
I think I have noticed one thing. I think we have a derivative product of the amount of workload we have on a read or a write bus. So Nancy, can you go to system config? And maybe pick up a row for 21st. If you look at it now, there is a 20% or 27% of the traffic read traffic. If you pump it up, say for example, the stream read to 80%. Now that goes to 100% of the power. And when you do multiplex with writes also, there is a row which calculates even the write performance. Can you go down? The 27 versus 13 So if you look at it, they are half to. Because of course you understand that the write bandwidth is half of the read. So when we do both 100 and 100, so the total power is 200. Of course. Yeah. So I think these are the direct implication on your power consumption.
So always when you deal with interconnects,
Exactly.
it's a big problem.
Yeah.
Interconnects consume a lot of energy all the time. Why is that? You remember the service? That's the whole problem. You try to squeeze a lot of data in one link, in one interconnect. To squeeze, you need to always double frequencies. If your input is 8, you need 3 times doubling the frequency. To 16, you need more to squeeze all the bits in one interconnect or communication. Thank you so much, Nancy. That was a quick exercise just to